Let's see if we know at given time intervals the velocity of an object if we can figure out how far it's traveled. So let's consider 2-second time intervals. So 0, 2, this could be in seconds, 4, 6, and 8. And now we know the velocity at these particular intervals. So maybe it's going 5 feet per second, then 6 feet per second, then 8 feet per second, then down to 4 feet per second, and let's go with 3 feet per second at the end. Okay, so how do we estimate the distance that this object has traveled? So if we look at these in intervals, so we've got 2 seconds here. And in these 2 seconds, we can estimate, hey, the object's been going 5 feet per second. And if so, over those 2 seconds, we can estimate that's 10 feet, right? Multiplied together. The second time interval of 2 seconds, between 2 and 4, we can estimate the object's gone about 6 feet per second. So that's 12 feet that it's traveled. The third time interval, we can estimate 8 feet per second. So that's 16. And then the last interval, we'll estimate another 4 feet per second to give us about 8. So what we're doing here, in effect, is creating a left-hand Riemann sum. Let's plot this to see what it looks like. Okay, so we have both a time and a velocity axis. So we'll call this V and this T. And at the T, we've got our 0, 2, 4, 6, and 8. And, let's go ahead and plot about where they are. So at the 0th second, we've got 5 feet per second, so it's, say, halfway up about here. The second one, it goes up to about 6 feet per second. At the 4th second, it goes up to about 8. So maybe something like this. And then at the 6th one, it comes down to 4, so way down here. And then the 8th one, it goes down further to about 3. And we can connect these to kind of give a sense of the trajectory of the velocity of the object. Now, the idea of the Riemann sum, if we're doing a left-hand one, is that you go to the left point and use that to kind of construct your rectangle. So if in this first 2 seconds, we're saying, hey, it's going about 5 feet per second, we go to the left-hand point and we make a rectangle as such. Now for the next point, we go with the 4, okay, we go to right about here, right? Because of the 4th one, we're looking at 6 feet per second. Now, when we go to the 6, okay, for the 6th one, we're actually taking a higher value, the 8, to make our rectangle. And same thing with the last one, we're taking a higher value of 6. So there's our left-hand Riemann sum. And so you can see that we're estimating the distance traveled. And so what's our estimation of the distance traveled? S, it's approximately, okay, I didn't quite put the markers in, but we can write it in. 5 times 2 is 10. And here we've got, it's always going to be times 2. We've got 6 times 2 is 12. And then we've got, this one's going to be 8 times 2, which is 16. And the last one is going to be 2 times 4, which is 8. Okay, so S is approximately, we add these up, 10, 20, 30, plus the single digit 16 is 46 feet. Okay? All right, so there's something very interesting going on here. And to try to drive it home a little bit, let me just create another plot. Okay? We've had this one, so let's just look at part of f of x squared. And, let's just consider x from 0 to 1. Okay, so we've got x between 0 and 1. And so this is now the path of the particle. We've got this parabola. And what we want to figure out, okay, so in this case, we're once again looking at v, the velocity, and t, the time. And so in this particular case, what we're saying is, you know what? We know the full path of the object, okay, say it's a particle, and that but for the 1 second, we have all the information. The velocity is, I'll write it out, v of t is equal to, now for if f of x is x squared, well here a variable is t, it would actually be t squared, okay? And the idea is, once again, we can figure out the distance s of t by using a Riemann sum, and we've seen that Riemann sums can be used to approximate the area under a curve. So the idea here is we can use the Riemann sum to get this area under the curve to go from the velocity to the position. Okay, I'm going to say it again. We can use a Riemann sum to go from the velocity to the position. And we've seen in a previous video that the Riemann sum, the area under the curve, can properly be expressed as an integral. Okay? It is the integral from 0 to 1 of t squared, the function, and we have these tiny, tiny rectangles, infinitely thin, are dt. Okay? But, there's a big but here. We already know something about v of t and s of t. Okay? We know that v of t is the derivative of s of t. The derivative of position is velocity. Okay? Distance is where your position is. So what this is telling us, hinting to us, is that if we want to go from the velocity to the position, instead of taking the derivative, it's an antiderivative. What the heck's an antiderivative? It's the opposite of a derivative. It's the inverse operation of a derivative. So if you're taking a derivative, and the derivative is t squared, how do you get there? Okay, well you need a higher power of t, like t cubed, right? Okay, so if we take the derivative of t cubed, we get 3t squared. There's no 3 there. And so the way that we deal with that is say, oh, if there's a 3 in the denominator, it cancels out the 3. Okay? So what we have just revealed is that integration, which is Riemann sums with infinitely thin rectangles, which is the area under a curve, is actually the antiderivative of the function. Okay? The only other piece that is sort of not it's missing from this is what about the 0 and the 1, right? So the v of t goes straight to s of t is t cubed over 3, but what about the 1 and the 0? And what you do, and we'll explain why, you evaluate it at the 2 points. So you evaluate it at t equals 1, and you subtract off t equals 0. And so when you do that, you do get that s of t equals, plug in the 1, that's 1/3. The 0 is 0, so it doesn't give you anything. It's actually 1/3. And so, precisely speaking, if a particle is moving within 1 second with a velocity that at every position is given by t squared, the total distance traveled is 1/3. If it's, like in this case, feet per second, it's traveled 1/3 of a foot. Okay? This is pretty amazing. Let's do another one, okay? So that we can get sort of the hang of this just a little bit. Excuse me. So let's say that we have, okay, so let's do an actual example. A function, okay? And the function, let's say, is, and you know, it could be f of x and it could be s of t, it could be v of t, right? Let's go with the velocity. Okay, so v of t is, and it's something like 3t squared minus 2t plus 1. And we want to know what's S of t, right? What's the position? So find, you could say like, you could say a lot of things. You could say like find, just find function, find S of t, where S of t is the position. Call it the position function. Okay, so what we just shown is that you integrate, but what it means to actually integrate is to take an antiderivative. So S of t here is actually the integral of 3t squared minus 2t plus 1. And the way you do that is just like a dt. Now, in this case, we had bounds from 0 to 1. The bounds will give us actual values, but for the function, you don't actually necessarily need bounds. It is simply an antiderivative. We want the antiderivative of this thing. That's what integrals are. They are antiderivatives. That's what the shortcuts mean. You know, you don't have to like do a Riemann sum and, you know, do limits. You know, you can take an antiderivative. And so you just ask yourself, what's the derivative at each of these points, each of these terms? Well, 3t squared, you just go to a higher power. It's t cubed. Now what about this one? Well, you've got a 2 and a t to the first. You've got to add one, so subtracting this t to the second. If you take the derivative of t to the second, it is negative 2t. And finding the last one, whose derivative is 1, is just t. Now, there's one little piece that hasn't been mentioned with this. What if I said plus 2? Or plus 3? Or plus 5? If you take the derivative of a plus 3 or plus 5, those all go to 0. So, whoa, wait a minute. Does that mean that any number you plug in there could work? It actually does. And you resolve that by putting a plus c, where c could in fact be any constant. Okay? So, this is we'll go over the fundamental theorem of calculus in detail, but this in effect is it. It's that the area under a curve is an antiderivative. And that's actually what integrals are. And so when you're first learning about them, you hear antiderivative, but people don't talk about antiderivatives, they talk about integrals. And it's known that integrals are antiderivatives. So more coming to kind of like flesh this out, but just to recap. So we started by looking at, okay, we've got time and we're looking at intervals of velocity and realizing, you know what, we can figure out the distance traveled if we multiply these intervals of time by the velocity, which works out to be a Riemann sum. And so we looked at another example and said, well, hey, if it's all filled in and it's not just approximate points, well, if we know that we get the position, say function, the distance traveled from like a Riemann sum, we can take the limit of those Riemann sums as n goes to infinity, write it as our integral, and using dt, the infinitely small rectangles times the function. But from our work in physics, we know that, let me just write this in here, that the derivative of s, so s prime, is the velocity, okay? And so what that means is it's like an antiderivative to go from s to v. S prime is v. Yeah, so you integrate the integral of v. That's my s. Integral of v equals s. So you integrate to go in the opposite direction. Because of the relationship, it's an antiderivative. It turns out that that works for any given function. Okay, this is incredible. Let's close out with the final example. And so, what is the integral straight out of the sine of x dx? Just by itself. Okay, so what we're learning, it's an antiderivative. You have to think, what derivative gives you the sine of x? Well, the derivative of cosine is sine, or derivative of cosine is actually negative sine. Now, there's not a negative there, so again, like you have to make little adjustments. You have to say, well, if you just write cosine of x, you're so close, but cosine of x is negative sine, there's no negative, so you just put a negative in, because then the negatives cancel out, right? Because just think of limits always. You can pull out the constants, you can pull out the negative one. Okay? So this is incredible. this is the fundamental theorem of calculus. This is the big reveal of introductory calculus. Integrals, Riemann sums, I'll say it again, they're antiderivatives. We don't have to compute limits. What we need to do is learn techniques to compute integrals. And the reason why I say learn techniques is because it is too easy to give an example that you cannot easily get the integral of. Just straight out, right? Like if I say, what's the integral of sine e to the x dx? Sorry, it's supposed to be e to the x power, but who knows? Because it's not like, is it, you could try something, is it sine e to the x? Is it cosine e to, it's like the chain rule messes things up. So integrals are actually more difficult than derivatives. You can't just take any integral. I mean, it doesn't have to be that complex, right? Like at this stage, we can say, what's the integral of just sine squared of x? How would you do that? And you might say, oh, it's sine cubed of x over 3. Okay, let's try it. Then you would get 3, everything's turning, my penmanship is going away, I'm overexcited about the fundamental theorem of calculus. You might think sine cubed x, but then when you take the derivative, that's 3 sine squared x times the cosine of x. The chain rule kinds of messes with things. And so whereas you can probably take any derivative now, you can't actually with antiderivatives. It's sort of a different ball game. That's the one that you're going to start to become proficient in.